Alright gang, here we go. This is for Chem 2 Unit 13. We're talking about voltaic cells and electromotive force. Should be fun time. Fun time. Alright, so previous couple of videos, we talked about recap of redox reactions and then balancing half reactions. So we were able to break up a reaction into its reduction part and oxidation part. And so these reactions are a little bit different than other reactions that we've learned about, because other reactions we've learned about require direct contact between the reacting molecules in order for them to have their chemical reaction occur. With redox reactions, we don't necessarily need that connection between the two. We can actually, all they really need is the ability for electrons and ions to flow between the two halves, and that's why it's important to be able to break them up into their half reactions. So if we have a spontaneous redox reaction, we'll talk about what that means in a couple of videos, but specifically spontaneous redox reactions, these electrons are transferred and we release energy. Alright, so here we've got two half reactions. We've got a zinc electrode and zinc sulfate, and then a copper electrode and copper sulfate. And because we've connected them with wires through our little multimeter here, and then through a salt bridge, we're able to create a space for these electrons to transfer. And because these electrons can flow, we can get a voltage difference, a potential difference. Okay, and so we call this a voltaic cell. So this is essentially just an overgrown battery is all we're doing. Okay, so if you've ever seen somebody taking a, making a battery out of like zinc and copper, like a nail and a piece of copper wire, and and turning it into a little lemon battery, it's essentially the same idea. Okay, so voltaic cells have two nodes, they called electrodes. One of them is the anode and one of them is the cathode. All right, the anode is marked with a negative, okay, negative, and the cathode is marked with a positive. Okay, oxidation occurs at the anode and reduction occurs at the cathode. To remember that, I have a saying, okay, un-ox, red cat. Okay, un-ox, red cat. So anode, oxidation, reduction at the cathode. All right, so un-ox, red cat. All right, so, but what occurs here, so we've got our anode has the zinc and nitrate solution. And then at the cathode, we have a hydrogen reduction. Okay, so the hydrogen is going from H+, so they have nitric acid in here, and it's being converted into hydrogen gas being collected in this little tube here. All right, and so what occurs here is that the anode, or at the anode, we have oxidation. Okay, and so this zinc is turning into zinc 2+. Okay, and these electrons are able to flow from the anode, and then they have a voltmeter, so you can kind of read it, and then down here to the cathode. Okay, and then it forms this hydrogen gas at the cathode. All right, and then, but the problem is, you could imagine like this anode here and the cathode, these electrons would go from one side to the other, and you'd get a buildup of positive charge on this side and a buildup of negative charge on the other. All right, and so you should know from your own experience in the world, or maybe you've taken physics, that in order for any way for electricity to flow, you have to have what's called a complete circuit, or a closed circuit. And so you need somewhere for these charges to get balanced. All right, and so in order to make that happen, here they're using called a U-tube. Yeah, it's just a tube shaped like a U, all right, and it contains like a salt mixture, okay, and we call this a salt bridge. All right, so this salt bridge is just a bunch of, in this case it's sodium nitrate, but it really could be any salt. And so this salt bridge here allows the transfer of ions in order to balance out these charges that are getting built up. So remember, at the anode, the electrons are leaving and we're forming a cation, and so the anion portion of the salt bridge will come and build up in solution down here. On the other side, on the cathode side, we're building up electrons, and the positives are leaving our solution. They're going and turning into hydrogen gas, which is neutral, and so we get a buildup of negative charges, and so the sodium comes in on this side. All right, and so we use the salt bridge to balance out these two. Okay, so this is essentially just walking us through what we've just talked about. And the cell electrons leave the anode, flow through the wire to the cathode. Cations are formed in the anode, okay, and anions are formed in the cathode. Yeah, in the cathode. All right. As the electrons reach the cathode, cations in the solution are attracted to the now negative cathode, and the cations gain electrons and are deposited on the metal cathode. All right, and so anyway, so our anode over time will lose mass because it's turning from, in this example here, was turning from solid zinc to zinc ion, and so this anode will eventually deteriorate and it will be gone. All right, it'll completely go away. And on the other side here, we'll just build up more and more hydrogen gas. And here they're using like platinum probably or something like that to help give the, a little catalytic area for this hydrogen gas to build up on. But in other reactions, could actually have like a buildup of metal. So if you like use silver and silver nitrate, you could actually have a buildup of metal on that silver. All right. So describing a voltaic cell. So let's see if we can do this real quick. So we've got this oxidation reduction reaction. We've got dichromate with, and they've already balanced it. All right. So, and we know that because we see these H pluses. So that's nice. All right. And yeah, so it says it's got a solution containing potassium dichromate and sulfuric acid poured in one beaker, and a solution potassium iodide is poured into another. A salt bridge is used to join the two beakers, and we've got a metallic conductor that will not react with either solution, and it's suspended in each solution and through a voltmeter to detect electric current. All right, and then the resultant voltaic cell generates an electric current. Cool. Now here's so all that was just info. And it says indicate the reaction occurring at the anode and the reaction occurring at the cathode, the direction of the electric migration and the direction of the ion migration, all right, and the signs of the electrodes. Well, they've actually already labeled a bunch of this stuff for us. So the anode is negative on this side, cathode is positive, electrons flow from the anode to the cathode through the voltmeter. All right, we've got our porous barrier salt bridge here. Anions are going to go towards the anode, cations are going to go towards the cathode. All right, so we need to figure out, essentially to answer the last part of this that's not answered in this picture, is we need to determine which reaction occurs at the anode and which reaction occurs at the cathode. And it's all based on unox red cat. So if we can figure out which one's oxidized, we know that happens at the anode. So our two half reactions is we got Cr2O7 minus, and that's going to 2Cr3 plus. All right, so we've got to figure out whether this is oxidation or reduction. All right, we could also start with I minus, right? I minus, all right, going to I2. Right, so we'd have two of these, and so which one would be easier to figure out? Well, if we do the top one, we'd have to mess with oxygens and then hydrogens, but if we do the bottom one, we can jump straight to charges. So I say let's skip the top one and do the bottom one. So we've got 2 minus here, which means we need 2 minus 2 electrons over here, and we're done. So the iodine reaction, half reaction, would be it's losing electrons, and remember oil rig, so oxidation is losing electrons, so our iodine is losing electrons, so it's being oxidized. So at the anode is the iodine reaction, okay, and then therefore at the cathode would be the chromium. All right, pretty easy. All right, last little bit here, electromotive force. Okay, so if you imagine a waterfall, water flows down through that waterfall spontaneously, right? Water starts at the top, goes down, falls down. You don't even have to think about it. It goes from high potential to low potential. And specifically in this case, it's talking about gravitational potential energy. Now, batteries work, and these voltaic cells work essentially the same way, only instead of gravitational potential energy, they use electrical potential energy. And so your electrons are going to flow from your anode to your cathode, from an area of high potential energy to an area of low potential energy. And this occurs because of those redox reactions we're looking at. All right. And so this potential difference between the anode and cathode is referred to as the electromotive force, or EMF. All right, and we measure this value as called the cell potential. Okay, and we call it the E cell, or the energy. In my head, I call it the energy of the cell, even though that's probably not quite right, but it's the cell potential E cell. All right, it's measured in volts, or potential difference. Okay, and 1 volt is equal to 1 joule per coulomb. All right, so that's your electromotive force. All right, now in the next video, we'll talk about standard reduction potentials, how we can actually use those chemical reactions to predict what that cell potential will be. Okay, it's not too hard, but it is a little bit different. So anyway, so stay tuned, do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.